All right. Welcome to the stream. Let's see if we can solve some of the hardest LeetCode problems. I'm filtering from 2500 and above. There are only 73 problems in this range. So let's start with the first one, maximum genetic difference query. Hey, Creepypasto, how's it going? How is your job going? Maximum genetic difference query. There is a rooted tree consisting of n nodes numbered from 0 to n-1. Each node's number, let me share the link, of course. Fine, I got promoted. I'm really happy in just 4 months. Yeah, congratulations. That's awesome. Okay, so that is the problem. Let's see if we can solve it. Each node's number denotes its unique genetic value. Genetic value of node X is X. The genetic difference between two genetic values is defined as the bitwise XOR of their values. You're given the integer array parents where, okay, so the rooted tree is given in terms of the parents, and the root of the tree has parent -1. You're also given the array queries, where queries I consists of node of I and val of I. For each query I, find the maximum genetic difference between val and p of I, where p of I is the genetic value of any node that is on the path between node I and the root, including both node I and the root. More formally, you want to maximize val of I return an array. Okay, so here we have an example. So here the root is node 0, and we have 4 nodes, and we have this queries. So for query 02, that means that for the node 0, we want to find the maximum with value 2, but you only have one option there, which is 0 XOR 2, right? And that is 2. So the answer is 2, that's correct. Now for node 3 and value 2, now you have so it's better to do XOR with 1, I think, because that's going to give you 3, and that's the maximum, right? And then for node 2 And number 5, so 5 is 101. And so probably 2 is the best. Yeah, x5 XOR 2 is 7, so that 7 is the maximum. So that makes sense. And we have a lot of nodes. Okay, what can we do here? So maybe we can work out this example. Let's see. So this is this. Anybody hiring entry-level dev? Not me. Anyway, so this is 0, 1, 2. So 2 is the root here. So this is 2. And we have, so yeah, let me do, can I increase the size of this? Okay, that's not. So this is 0, 1, 2, 3, 4, 5, 6, and 7. So 3 and 7 have 2 as a parent. And then 0 has 3 as a parent. And then 4 and 6 have 0 as a parent. And then 7 is the parent of 5. And then, so I have 7, I should have 8 nodes. So what am I missing? Yeah, I have 1 that is also a child of 7. Okay, so this should be it. Does it match what we have here? Yeah, 1, 5, 7, 1, 5. Yeah, so our queries are, so for query 0, we have 4 and 6. So 4 is the node, right? So we're here, and we want to find, we want to XOR with any of the values in this path, right? From 4 to the root. So we go here. So there is a way. This is a known problem. So to quickly find, so we cannot we cannot, obviously, we cannot do this quadratically, right? Because there are up to 10 to the 5 nodes. But if we have all the values in the path to the root in some data structure, maybe we can find the value that will give us the maximum XOR. And that is a known problem, which you can use the data structure that is useful for this is, so notice it's a trie of the binary digits. So notice that since we're doing bitwise operations, then it's better to express the numbers as in binary. So let's say, so this is 2, so will be this is 3, so in binary it is this is 0. I'm just using 3 digits, and this is 6, which is 1 0, and this is 4. Okay, so what if we had a trie data structure where we had all the values in this path? So for example, we would have we would have the root, and here we have we have a 0. So this start from the most significant bit. Now you're going to see why. But here, for example, if we're adding 2, then we have a 0. I must go to sleep. I'm going to check the video later. Good night. Nice to see you as always, coach. Thank you. Yeah. Yeah, I'm trying to explain. So I'm trying to do problems that are challenging for me, and at the same time I'm trying to explain them, as make them as easy as I can so that they can be understood without having much previous knowledge. So that is my goal with this kind of stream, but it is a challenge. I'll give you that. So here's 0, but yeah, have a good night. 0 1. So now we have a 1 here, right? 0 1 and 0. So this will be our 2, right? 0 1 0. And then 3 for 3 is 0 1 and then another 1. So this is 3. And then for 0, it's 0 0 and 0. So here's our 0. Notice that in the trie data structure, it's better to think about the edges as having the numbers or the letters if it's a letter trie. But here we only have 2 options, 0 or 1, because it's the binary digits. So again, and then we have 4, which is a 1 first, then a 0, and then another 0. So 0 0, and here's our 4. So okay, so this is our trie data structure. When we are here, when we are at this node, we want to keep track of all the numbers in the path. And now we have our val is 6, which in binary is sorry, it's not, that's 5. is like this in binary, right, in base 2. And so we can process from the most significant digit, the most significant bit, right? So the first one is here. So we have a 1, right? So if we want to XOR, if we want the XOR to be maximum, we would like to have a 0 here. We want to have a different bit, because and since this is the most significant one, this takes priority over anything else, any of the other digits. So we would like to have a 0 here. So that means, and we do have values that go to this this side of the trie, and so we go over there, right? So now we're here, and now we again have a 1, right? So now we again want a 0. So, and there are values to that side, so we continue, right? And then here, now we have a 0, so we prefer a 1, but there is no 1. So then we have to go to 0. And then, so the answer is 0. Like this value is the best one. And the XOR, so we end up doing, well, this XOR 0, and we get 6, right? So the answer to this query is 6. And let's check if it's right. Yes, it's right. It's 6. That's cool. And so notice that when we are deciding whether to go left or right, to go 0 or 1 in the trie, we want to know, we're asking whether there are any values. So we prefer one of the values. So we prefer the value that is different from the bit of the query value. But we want to know if there's at least one number in that side of the trie. And for that, what we can do is, because notice that when we are traversing the tree, we are going to keep adding. So when we go down this path, we're going to add here the 4, and then when we go up, when we will go back, we're going to remove the 4. And then here we add the 6, and then we remove it. So we're going to need to be making to have an add operation and a remove operation from the trie. So that means that we cannot just depend on whether there is a node to know if there are elements on that side. So what we can do is we can annotate every node with the number of elements in that subtree, right? So here we added 4 elements. So here the subtree, which is the whole trie, will have 4 as the size. And here this one is going to have 1, and this one is going to have 1, and this one is going to have 1, because there's only 4. Only 4 starts with 1. But here we're going to have 3, 2. Of course, the leaps are always have 1. And here here there's 1 and 3, right? So now we have annotated with all the sizes of the subtrees, and that's how we're gonna know how to where to go to find the best value to pair the query value with. Okay, so yeah, I think once we have that, so let's work out another query. So now we have query 1, which is 1 and 15, and yeah, and 15, so 15 equals to yeah, so it's 8 plus 4 plus 2 plus 1, right? So 12, 14, 15, right? So this is 15. So yeah, here there's a problem because I didn't do this, and yeah, you have to first know how many bits there. So let's check out how big these numbers can be. So the values can be up to 200,000, and yeah, this is these are the numbers of the nodes, which are also bounded by. So yeah, the values are going to be smart coder. Welcome. So the values are going to be bounded by 200,000. I think. What was it? That I already forgot. Yeah, and so I think so. So we have 128k, which is 2 to the. So this is 17, I think. 2 to the 17. So this is the largest power of 2 that is going to be that it's not going to exceed the maximum value. So that means that we want bits from bit 0 up to 17. So we want 18 bits. Okay, that's how many bits we care about for our trie. So anyway, so let's solve this query. So now we're at 1, right? So we're here. So this is the path that we care about, right? And so this is 7, which is 1, 1, 1. So 4, yeah. And this is 1, which is 0, 0, and 1, right? So now our trie would be something like this. So we have here we have a 0, and then we have 0 and 1, right? So 0, 0, and 1 is going to be this value, the 1, and then 0, 1, 0 is going to be the 2, and then the 7 is going to be 1, 1, and 1. Right? So this is our 7. So this is how our trie looks looks now for this query. So now, here we want the first one to be a 0, and it is. So this is going to be a 0. Then here we also want a 0. Then we also want a 0 for the next one. And then we also want a 0 for the last one, but we don't have it, so we have to have a 1. So in summary, the best is to XOR this with 1, and we're gonna get this number, which I think is 14. And yeah, so this is the answer of this query. Okay. So you get the idea, right? We have to maintain a trie data structure with binary digits, right? And so what else do we do? So we have to transform first the tree in an adjacency list, right? So that we can traverse it with a DFS. And then I think we're gonna need, so for the queries, we're gonna need to have them in in some data structure. Yes, I guess we could have a list of lists, right? So that we have all the queries for each node in the position of that node, the index of that node, and then we can process them all together. So yeah, I think with that in mind, we can actually code this. So we said that we needed 18 bits, right? And we're gonna have a trie data structure. Which is going to have the pointer to the next node, which initially is going to be none, and the count of the number of values in this subtree. Okay, and so we need to be able to add or remove. So I think we can make an add function that has the trie and has the value and a delta. Yeah, I think it makes sense. And so now we want to go over the bits from largest to smallest, from most significant. And so this is going to be our bit. So we shift I and we end with 1. So this is our bit. And now we want to if t dot next of b is none, then we have to create a new node, right? Whoa, it's rated. Yeah, that's the idea here. I'm trying to find problems that are challenging for me so that I can learn, and then I try to break them down so that you can so that anyone can understand them without much knowledge. So I started right here, right from the beginning. There are 73 problems of this level and above. So I have quite a few to do. Okay, so here we create a new node, and then we go to the next node. Yeah, so T is this, and so now we want T count to be incremented by delta, right? And there's a special case here. We want the count of the root to also be incremented by delta. I don't think that matters actually, but let's keep it consistent so that all the nodes have the size of the subtree, the count of elements in the subtree. So now we have our add, and maybe for convenience to make it nice, we can do a remove that just calls add of tx and delta equals -1, right? And so now we have our add, our remove, and we want to create our adjacency list. So the number of nodes is the size of parents, and so we're gonna go. So if if parent of u is different than -1, then we want this, right? And otherwise we want that means that the root is u, so let's save it. Okay, that makes sense. So now we have it in a way that we can traverse it with a DFS. But we also need to do something with the queries, right? We want to have them, so we want to change them. Yeah, so let's say that M is the number of queries, and we're gonna have a res of that size, and then we want to have queries. Yes, so let's call it so the queries are for a node, right? And there could be more than one for the same node, so that's why we want to. So this is the node, and this is the value, and so we want the query to be be here, but we also want to know the index so that we then set the res in the right position, right? So here we want to have the value x and the index of s. So now we want our DFS. And we don't need to worry about, so this is a tree, so we don't need to worry about the going back to the parent, so I don't think we need that. So we're gonna do a DFS, right? And now we go over the children of U. And of course we have to keep track of the, we have to create the trie. So oh, we already had a root. So this is our trie. Yeah, maybe call it path. And so here we want to add to our path b, right? We want to add b. Then we want to call recursively. Then we want to remove b from the path. And here we're going to answer all the queries for, so this is going to be all the queries for U. Okay, so we want to, let's do, so this is the index, and let's do, let's have a function that, given the trie and the value, is going to give us, yeah, let's call it max XOR. That it's going to give us a value that we want, that we're looking for. And here we call DFS with the root, and then we return res. Okay, so now we need to do the max XOR with a trie, and this is the value that we care about. And so we go over the bits from largest to smallest, from most significant to least significant. And here we just, yes, so we get the bit. And now we want to know if we have the opposite bit, right? Because that's the one that's going to create the maximum XOR. So we check if t of next of 1 minus b equals, yeah, I guess it would be, it's better, it's more, this is better to just flip the bit, I guess. So if this is none, then we cannot get the, we cannot get a 1 in this bit. So in that case, t is going to be t of next of b, right? Yes, we're gonna have the same bit here. else, in this case, we do want to set this bit in the result. We are able to set it, and then this is going to be our next node. But here there's another option. So if it's none or the count is 0, I guess, right? If there's, because you could have the node, but if there are no elements there, then you don't want it. You can't get it either. So now here we return the result. Okay. What's going on here? Oh, what the hell? Parents. So this is parents. Okay. Just some typos. And here, oh, I forgot to do the iterate. And here, so T is none. That shouldn't happen. So here, so there must be, oh, I guess there's a special case for the root. Oh, no, wait. Yeah, there's something special here. So yeah, I think I'm not handling, so I think I have to add the root. Yes, I'm not adding the root to the path. Yeah, I think it's a special case. I don't like that, but I guess it's okay. Let's see. Cool, it passes the examples. That's surprising. I think was quite a bit of code. So let's see if it passes. Let's see. And we got it. Cool. We got it. Yeah. Clap. Thank you guys. Did you follow the bitwise trie? Yeah, that's one you should remember. Because I mean, this comes up, the finding a value from a set such that the XOR with a given value is maximum. This is the way to do it. Then this has the complication of having the tree and having to keep track of the path to the root. and so on. But yeah, I think this one, I guess this one is a little known. So the contest, I think I would get it. But I guess it has this rating because not many people know the technique or knew the technique during the contest. So this is quite an old one, I guess. So we have like 50 weeklies for year, and now we're almost at 400. So this is like 150. So 3 years ago. So yeah, maybe people now are better. Okay. Maximum sum queries. Oh, it's been 50 minutes. Okay. That was longer than I expected. Maximum sum queries. Maybe you should title the videos with proper titles. I was planning to do more than one problem. I don't know. So but I don't know. I'm gonna read this one and see if I have an idea, or otherwise I might leave it for tomorrow. Maximum sum queries. You are given two zero index integer arrays, nums1 and nums2, each of length n, and then queries with x and y. Find the maximum value of nums1 of j plus nums2 of j, where nums1 of j is greater than or equal to phi, and nums2 of j is greater than or equal of y of I. Return an array answer. Okay, with the answers to the queries. So the sizes are 10 to the 5. And the values are 10 to the 9. So I guess we can think about this as coordinates. Nums1 and nums2 can be x and y. So what are they really asking? So we have to find so x, y, right? So we're given an x, xi, and yi, and find the maximum value of the sum among all indices Okay, so we have to search for so we have this and this, and we want to consider the points that are here, right? And so here we have a point, and we want the one that has the maximum x plus y. So what does that mean? So I guess for these kinds of problems, usually you can sort by one of the coordinates and process them in order. Like we could sort by x, so that we go from largest to smallest x, and so when we process the query for xi, we already added all the points that have an x greater than or equal to x of I into some data structure, and then we try to find quickly in that data structure. So we have so it would be, but what data structure can we use to maximize this max? So the max. So if we have a point here, wait. Okay, I'm gonna leave this one for, I'm gonna continue tomorrow because I've already done an hour of stream. So thanks for watching and see you tomorrow. Bye bye.